So we're going to talk a little bit more about energy. Remember, earlier we defined energy as being the capacity to do work. And we said work is a force applied over a distance, and the force is mass times acceleration. And we talked about those things. So now we're going to talk about this energy, this capacity to do work. Now, remember there's two fundamental types of energy, kinetic and potential energy. Now, we're going to talk about thermal energy in this chapter quite a bit. And what thermal energy is, it's the kinetic energy of the particles that comprise a substance. What does that mean? Well, every object, every substance that's at any temperature above absolute zero, the atoms or the molecules in there, they're moving. Even if it's a solid, those atoms are vibrating, oscillating as if they're connected by springs. And that's a kinetic energy, and that kinetic energy is their thermal energy. Now, if it's a liquid, then the particles that make up the liquid are moving around. They stay in contact with each other, but they're moving around all the time. That's kinetic energy. If it's a gas, they're flying all over the place. Still kinetic energy. And that's the thermal energy we're talking about here. And the more thermal energy a substance has, the hotter we say it is. Now, when we say the word heat, this means something specific. It's a process. It's the process by which we transfer this thermal energy. Now, if you put something hot next to something cold, the hot thing will get cooler and the cold thing will get warmer. That's because the thermal energy spontaneously flows from the one with more thermal energy, the hotter one, to the one with less thermal energy, the cooler one. You can think about heat as like rain. It's a good analogy. Rain is the process by which rainwater falls from the clouds in the sky to the ground. You can't touch rain because it's a process. You can touch rainwater, but not rain. That's a process. Just like heat. Heat's the process by which this stuff, thermal energy, is transferred. Now, having said that, almost every textbook uses heat to mean thermal energy when they're talking about it. Now, we're going to talk about the distinction between what we call the system and the surroundings, because we're going to look at thermal energy being transferred between different things in this chapter a lot, and we're going to define whatever we're interested in as the system and everything else as the surroundings. Now, you can define whatever you want to as being the system. Usually, almost always, we define the system as whatever it makes it easier for us to figure out what we're trying to do. It could be a solution. It could be just the chemicals in a reaction, whatever you define it as. Now, in an open system, both matter and thermal energy can be transferred between the system and the surroundings. So like a beaker of water. So the water molecules can evaporate and go back and forth between the surroundings and the system. The system, let's say, is this inside the beaker here. And also thermal energy can be transferred. If we put put this on a hot plate, thermal energy will go from the hot plate into the water. We can also have a closed system. In a closed system, matter cannot be transferred into and out. It's closed, so none of these water molecules can escape. Nothing can go in. But you can still transfer thermal energy. You can make it warmer or colder. Now, in an isolated system, which is the hardest to make, but sometimes the best for what you're trying to do in chemistry, neither thermal energy nor matter can be transferred into or out of the system. So, you put it in a vacuum, suspend it in a vacuum or something like that. Now, some more terms, exothermic and endothermic. When we say exothermic, what we're talking about is a process that releases thermal energy. For example, combining gaseous hydrogen and oxygen to make liquid water gives off heat. It combusts and it gives off quite a bit of heat, really. An endothermic process is a process that absorbs energy. The system absorbs energy. It ends up that when mercury 2 oxide decomposes into liquid mercury and oxygen gas, it's an endothermic process. It absorbs energy. Now, if an endothermic process occurs spontaneously, and say it's in a beaker that you're holding, that beaker will feel cold. The reason is that the system is absorbing thermal energy from that beaker in order to do the reaction. An exothermic process, to you, if you're close to it, feels warm. You can feel thermal energy being given off. Now, units of energy, because we're going to be using these a lot. A calorie, the symbol is CAL, and it's calorie. and it's equal to 4.184 joules. Joules is another unit of energy. I should write these out. So calorie is CAL. Joule, it's a capital J named after a guy, stands as a unit of energy. This is the conversion between the two. You should memorize this. 1 calorie is equal to 4.184 joules, and that's an exact relationship. It's a definition. Now we have a big calorie. Notice that only the difference between here and here is just a capital C, and a big calorie is really just a kilocalorie. It's 1,000 of the little calories. When you read a food container, it tells you how many calories are in one serving of that food. That's the big calorie. This is also called a nutritional calorie right here. Now the other unit of energy we have that we'll see once in a while is a kilowatt hour. Let me write that down. kWh. And that's equal to 3.6 times 10 to the 6th joules, and that's an exact relationship also. Memorize these guys. Put them on your card. Next, states and state functions. So yeah, this module we're just doing a bunch of definitions really, but that's okay. So when we talk about the state of the system, any system, it's defined, this state, it's defined by what values the properties of that system have. Things like its energy, its temperature, its pressure, volume, what's it made of. Like that's the properties, and the values of these define the state of that system. Now when we talk about a function, it's a property, one of these properties, that only depends upon what state the system is in and not how it got there. Now, it's going to be real important to us that energy, temperature, pressure, volume are all state functions. Their value depends upon only where they are and not how they got there. So for example, if we take a beaker of water, it's at 22 Celsius, we heat it up to 98 degrees Celsius, cool it down to 14 degrees Celsius, and then heat it up back again to 73 degrees Celsius. Its temperature is 73 degrees Celsius. It doesn't matter that it went all over the place trying to get there. It would be the same as if we started at 22 Celsius and warmed it directly up to 73 Celsius, right? You see? It's a state function. Now, because state functions only depend upon the state of the current state of the system, the change in a state function, the change in the value, the delta of a state function only depends upon the final and the initial states. Here's a real good analogy in this picture right here. Let's say your function, your state is what floor you're on, and the change in your state would be, how many, the difference between where you started and where you ended. So let's say you're on the ground floor, and you climb up to the 4th floor. So you've gone up, 1, 2, 3. I don't see how that's the 4th floor. I think that's the 3rd floor. But anyway, 1, 2, 3. No, there it is. 1, 2, 3, 4. That's the 4th floor. So you went up 4 floors, right? Now, your change in your elevation is just 4 minus 0 is 4, I guess. If you went up to the 2nd, the 3rd, the 4th, the 5th, the 6th, climbed up on the roof, danced around a little while, jumped down, climbed back up, climbed back down, did another dance down here, and then went back up to the 4th floor. Your change in your elevation is still 4 minus 0 is 4, right? Doesn't matter.